In this video, we continue to look at basis representations, and we will also look at dimensions. These are topics from chapter 4.5. So in the last video, we saw the uniqueness of the basis representation. Essentially, we saw that if S is a basis for a vector space V, then every vector can be written in only one way as a linear combination of vectors in S. So let's take a look at an example modeling this. So using this basis that we saw in a previous example, we showed that this was linearly independent and spanned R3, so it meets the definition of a basis. We are going to find the unique representation of U, where U is generic in terms of U1, U2, and U3 using this basis. So in other words, we are going to find the unique solution for the constants C1, C2, and C3 in the equations in terms of the components of U. And then for an arbitrary vector, you could plug in the components in place of U1, U2, and U3. So here is U. It is going to be represented as constant C1 multiplied by the first part of this basis, 7, -2, 5, then C2 multiplied by the second part of the basis, -3, -9, 1, and C3, the scalar constant, multiplied by the third part of the basis, 1, 7, -7. So we can translate this into a matrix. We can put the first part of U, we'll call it U1. Well, let's not call it U1 actually, because U is already U1, so we'll call it maybe V1. Okay, so we'll call this V1, V2, and V3 as the vectors forming our matrix here, what we think of as our coefficient matrix, multiplied by these scalars, C1, C2, C3, to give us our unique representation, U1, U2, U3, that comprise vector U. So working backwards, we know we can solve for these constants, C1, C2, and C3, by using the inverse of our matrix here that corresponds to V1, V2, V3, the vectors that make up the basis, multiplied by U1, U2, U3. So we end up here with a formula that you could use to find each constant, C1, C2, C3, depending on the individual components of vector U, U1, U2, U3, where U is an arbitrary vector. So we see this is unique. There's a unique equation to find each constant C1, C2, C3. And note I'm using constant and scalar kind of interchangeably here because our scalars here are from real numbers, so they're what we think of as constants. Theorem 4.10 is about the relationship between bases and linear dependence. So if S is a basis set of vectors V1 through Vn, and it's a basis for vector space V, then every set containing more than n vectors in V is linearly dependent. So in our proof, we're going to let S1 consist of a set of m vectors, U1 through Um, and it's going to be any set of m vectors in V where m is more dimension than n. So m is greater than n. There's extra vectors in here. So to show that S1 is linearly dependent, you need to find scalars k1 through km where they're not all zero, so it's not empty, such that k1 u1 plus k2 u2 through km um equals 0. We're going to call that equation 1. We know S is a basis for vector V by our assumption. So since S is a basis for V, each ui can be represented as a linear combination of the vectors in S. So here's u1 through um represented as linear combinations of vectors v1 through vn. Then we can substitute that back into equation 1. So remember, equation 1 was the constants k multiplied by u1 through um. Then we can regroup and say, well, this is just this equation d1, v1, d2, v2 added through dn, vn, where the d's represent now constants C through constant C, what we'll call I1 multiplied by K1. So some of the C's must be recycled in here, right? Because there's more K's than C's, because K has M components and M is more than N. So that's why we're using the subscripts on these C's, like CI1, CI2. So some of the C's are duplicated. Okay, so the VI's, we know, form a linearly independent set. So each DI equals 0, and you get this system of equations down here where the coefficients here, the C's multiplied by the K's, are all equal to 0. Excuse me. So this is a homogeneous system that has fewer equations and variables. So we've got K1 through Km, but that's a problem because there are less equations. There's just n equations here. Notice these are C1 through Cn here. And then we know from Theorem 1.1 that it's going to have non-trivial solutions. So then S1 is a linearly dependent set. It also makes some sense because you think if you've got extra equations in there, if m is greater than n, then you're going to have some extra combinations. So that's what we've shown in here. All right, let's look at an example illustrating this. This is example 7 from the text. So we're going to show two linear dependent sets. So R3 has a basis consisting of 3 vectors. We know that. The standard basis in R3 is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So if we take these 4 vectors in R3 as a set, they must be linearly dependent because the dimension 4 is greater than the 3 vectors that form the basis. Similarly, P3, the set of all polynomials of degree 3 or lower, has a basis consisting of 4 vectors. So if you take this set here with 1, 2, 3, 4, 5 vectors, you know you're going to have some linear dependence in here. In general, Rn has the standard basis consisting of n vectors, so it follows from this theorem that every set of vectors in Rn containing more than n vectors must be linearly dependent. So this brings us to the idea of the number of vectors in a basis. So if a vector space V has one basis with n vectors, then every basis for V has n vectors. So in our proof, we're going to let S1 be the vectors V1 through Vn, and those are a basis for V. And then we're going to let S2 be the vectors U1 through Um be another basis for V. Theorem 4.10 implies that M is less than or equal to N because S1 is a basis and S2 is linearly dependent. But similarly, N is less than or equal to M because S1 is linearly independent and S2 is a basis. So the only possibility here is that N equals M and there is a set number of vectors and a basis. So if you have a basis of n vectors, then every basis has n vectors. So this brings us to this concept known as dimension. So if a vector space has spaces consisting of n vectors, then the number n is called the dimension of V, and it's noted this way. We say dim of V equals n. And we define the dimension of the trivial vector space, the 0 vector, to be n equals 0, even though there's an element in there. We do that so that when we build up things that actually have one element, will be n equals 1 with one non-zero vector. The dimension of a vector space is well defined, or in other words, unambiguous, because of Theorem 4.11 here. That we've shown that if a vector space has one basis with n vectors, then every basis has n vectors. Here's some examples. The dimension of the real numbers in n dimensions, Rn, is n. That makes some sense because you've got n dimensions there. The dimensions of the polynomials sub n is n plus 1 because remember you've got x through xn, but then you've also got the constant term, so that constant term is where the plus 1 comes from. And then the dimension of the m by n matrices is m times n, and we saw that back when we saw our standard bases example. So in our standard bases example, we saw the standard basis for the 3 by 2 matrices had 6 elements because you had to have a 1 in all the unique positions and zeros in all the other positions, so that gave us 6 elements there. And then down here, the standard basis for the 2 by 2 matrices had dimension 4 because we had 4 different positions you had to rotate the 1 through in the matrices. So because of the 2 dimensions of the matrices, rows and columns, we have m by n dimensions for the set of the vector space. All right, in this example, we are going to find the dimension of the subspace of R3 given by W, where W equals 2A as the first element, A minus 3B as the second element, and A plus B as the third element, and A and B are real numbers. We're in R3. So we can factor the A's and B's out and rewrite this as A times 2, 1, 1 plus B times 0, negative 3, and 1. So that W is spanned by S, where S is the set of vectors 2, 1, 1, and 0, negative 3, 1. Moreover, S is linearly independent because if we put this into reduced row echelon form, we get 1, 0, 0, 1, and then zeros in the bottom row. So every column here has a pivot. So the only solution is if A and B are 0 for setting this equal to 0 over here. So the only way to get the 0 vector out is AB equals 0. So S is a basis, and the dimension of this W, the subspace, is 2. So this is 2 dimensions. And that makes some sense because we could see here, when we look at the original set W, that A and B were dependent in that third component. Here in example 11 from the text, we're going to look at finding the dimension of a subspace. So let W be the subspace of all symmetric matrices in the set of all 2 by 2 matrices. We call that M with a subscript of 2, 2, where the rows come first and then the columns. So what's the dimension of W? Well, every symmetric 2 by 2 matrix C has the B's in common on the outer diagonal, as I might call it, or we could say the B's are in common in both row 1, column 2, and row 2, column 1 for the symmetry. So our matrix to multiply B by is 0, 1, and 1, 0, and A and C go with these matrices with unique elements for A and C are. So this set of these 3 2 by 2 matrices spans W because W is a subspace of symmetric matrices. Moreover, S can be shown to be linearly independent, and so you can conclude that the dimension of W is 3. So it is dimension 3 and not 4 because of this limitation that they are just symmetric matrices and they're subspace. That brings us to theorem 4.12, which is about basis tests in an n-dimensional space. So if V is a vector space of dimension n, then we have 2 properties here. So the first property is that if S is vectors v1 through vn, and it's a linearly independent set of vectors in V, then S is going to be a basis for V because V has dimension n. And then the equivalent property is that if S equals v1 through vn spans V, S is also a basis for V. So these are 2 ways to show that a set is a basis. It can be linearly independent and the same dimension, and it can be spanning V in the same dimension. So let's look at the proof of part 1. So if S is v1 through vn, and it's linearly independent, and it's a set of vectors in V, then suppose by way of contradiction that S does not span V. So this is going to be a proof by contradiction here. Well, then there would be some other vector v in the vector space that's not in the span of those n vectors. So then the set v1 through vn with this extra vector v is linearly independent, but that's impossible because now we've got dimension n plus 1. And we know from theorem 4.10 that every set containing more than n vectors is linearly dependent. So S does span V, and therefore it's a basis. Remember, to be a basis, it has to both be linearly independent and span. So that's why we've shown that this spans, because we already had the linear independence property. Part 2, we're going to assume that S is V1 through Vn and it spans V. So suppose by way of contradiction that it were dependent, then there'd be some vector Vi and S that's a linear combination of the other vectors. But then we could assume that Vn is a linear combination of V1 through Vn minus 1. We say without loss of generality because if it wasn't Vn, it might be V3, and then we'd still have n minus 1 other vectors. So when we sort of arbitrarily pick a generic vector to stand in, we're able to make this statement without loss of generality. So if that were true, then V1 through Vn minus 1 would span V, but that would be one short on the dimension needed. So we know n minus 1 vectors span a vector space of at most dimension n minus 1, so that's a contradiction. So then S is linearly independent, so we already had that S span V. If it's also linearly independent, then it's a basis. So what we get out of theorem 4.12 is if you have the dimension n, then if you've got a linearly independent set of n vectors, you have a basis. And if your set is, your vector space is dimension n, if you've got a set of n vectors that span V, you also have a basis. So you don't have to check the linear independence if you've got case 2, and you don't have to check the span if you've got case 1. So if your dimensions match, you only have to check one of these properties.